Why coordinate system? In electromagnetic, there are number of physical quantities which are functions of space and time. Special variations of the quantities. Special variations of the quantities means we are writing deva by deva x, that is the partial derivative. So change with respect to only one direction, that is x direction. Deva by deva y means change with respect to only one direction, that is y direction. So these are the special variations. So in electromagnetic, we are considering special variations, that is variations with respect to space and also variations with respect to time. We must be able to define all points in space in a suitable manner. This requires using an appropriate coordinate system. Now, coordinate system, why it is required? Because if you want to define a point in a space, then to define a point in the space, what is required is called coordinate system. And coordinate system, there are two types. One is the orthogonal and second is the non-orthogonal. But non-orthogonal coordinate system is slightly complex and it is very difficult to implement. So generally we use orthogonal coordinate system. And in orthogonal coordinate system also there are number of types, but we generally consider three coordinate system, that is Cartesian coordinate system, cylindrical, that is circular cylindrical coordinate system, and third is the spherical system. So these are the three coordinate systems we generally use. Now, even though there are three different coordinate systems and we generally use this three coordinate system in electromagnetic theory, but the concept behind all coordinate systems are same. Once we understand the concept behind one coordinate system, suppose if you understood the concept behind Cartesian coordinate system, then you can easily implement the same concept for the other coordinate system. So what do you mean by concept? Concept means there are two things basically. One is a procedure to finding dot or cross product of two vectors in a cylindrical coordinate system is the same as that used in Cartesian coordinate system. So once you understand what is the how the dot product is calculated or cross product is calculated using a Cartesian coordinate system, then same concept you can apply in other two coordinate systems. And sometimes it is necessary to transform. Suppose if you want to transform a point or a line from one coordinate system to another coordinate system, then how to transform that line in another coordinate system. So that time the coordinates will be different. So like that you have to you should understood what is the how to transform and how to what we call how to find the dot product, cross product, like that. So these are the basic things which are needed to understand the coordinate system. Now we'll go for Cartesian coordinate system. Now this is also called a right-handed means as you know, we generally use a right-handed screw rule. So A cross B is equal to C. So when A moves towards B in an anti-clockwise direction, then direction of C is upward. So right-handed screw rule we generally use. And in the matrix form, how we are writing? We are writing AX, AY, AZ in the first row, that is unit vectors which shows the direction. Second is the magnitude AX, AY, AZ and BX, BY, BZ. And here in Cartesian coordinate system, when we are defining the vectors, that time we should know that there are two types of product. One is the scalar triple product and second is the vector triple product. So output of scalar triple product, why it is called scalar triple? Because output, the result obtained is a scalar, and hence it is called a scalar triple product. Now here how we are writing, that is written here. So when you are writing A dot B cross C, then how we should write? So B dot C cross A, or it is also equal to C dot A cross B. In vector triple product, A cross B cross C is equal to B into bracket A dot C minus C bracket A dot B. When we solve numerical problems based on electromagnetic field, that time these three equations are required. Now this is first we should understand what is Cartesian coordinate system. And in Cartesian coordinate system there are three axes, x, y and z, and these three axes are, since it is an orthogonal coordinate system, these three axes are perpendicular to each other. So what is the range? Range is minus infinity to plus infinity for all these on all three axes, that is x, y, z. And if you want to define any vector, a vector A, suppose if you want to define in a Cartesian coordinate system, then it can be defined as ax into ax, ay, az, az. So ax, ay, az, these are the unit vectors. I hope you understood what is the meaning of unit vector. So this unit vector denotes the direction, and ax, capital AY, capital Az, that indicates the direction of the magnitude of that vector along that axis. So here we'll see about the second coordinate system, that is circular cylindrical coordinate system. Now when we solve numerical problems related with cylindrical shapes or cylindrical symmetry, that time we use circular cylindrical coordinate system. Now here first we should know how to define a point P in a cylindrical coordinate system. Like in Cartesian coordinate system, it is defined as ax, ay, az or x, y, z. So here it is represented by p phi z. Now these we need to define is the space variables. So which are the space variables? So first is the radius of the cylinder. So here it is denoted by a small letter, that is rho, or it is purposely defined as a rho because we want to define a point P. Okay, so point P and rho, that should be different, that should be able to differentiate. That's why we have written it as a P. So P is the radius, which is nothing but a distance. So 0 to infinity, because we define center at the center at origin. So center of the cylinder at the origin. So P is the distance. It is defined from 0 to infinity. Phi is the angle made by x-axis. Made with the x-axis, so it is you can increase it from 0 to 2 pi, since it is cylindrical, circular cylindrical, so it is from 0 to 2 pi, and z is the distance, that is from minus infinity to infinity. Now this is about the point P. Now how to define a vector in a cylindrical coordinate system? So it is defined as AP. So AP, second AP, that is a small AP, that is nothing but a unit vector. So it is AP multiplied by a unit vector. Same way, plus Fi plus Az. Now how to find a relation? Now sometimes it is required to find a relation between cylindrical coordinate system and Cartesian coordinate system. So when you need to transform from Cartesian coordinate system to cylindrical coordinate system, that time we need to define the relation. So the relations P in cylindrical coordinate system is defined as square root of x square plus y square. Second, phi, that is the angle made with the x-axis, that is defined by tan inverse y by x, and z will remain same. In the same way we can write x is equal to p cos phi, y is equal to p sin phi, and z is equal to z. So this is about the cylindrical coordinate. In the previous slide we have seen about point to point transformation. So the point given in Cartesian coordinate, if you want to transform in cylindrical coordinate system, then we have written the equation, and using that equation you can transform the point. But let us say we want to transform a vector from Cartesian coordinate system to cylindrical coordinate system. Then how to transform it? So we'll derive some equation using using this diagram of cylindrical coordinate system. Here we have defined AP, Fi, Az, and using these directions and the angle phi, we can derive the equation, or write the equation AP is equal to ax cos phi plus ay sin phi. Since it is in xy plane, you can directly write ax cos phi and ay sin phi. While writing a phi, we'll see the direction of a phi and ax. So we'll get minus ax sin phi plus ay cos phi. And third is the az will remain same. So these are the three equations. Now these three equations you can write in matrix form. So in the matrix form it is written, and again if you want to transform from Cartesian cylindrical coordinate system to Cartesian coordinate system, then what you will do, you will find the inverse of the middle matrix, that is cos phi sin phi 0. Since in the third column two zeros are there, and in the third row also two zeros are there, and it is a 3 by 3 matrix, so you can directly write cos phi minus sin phi 0 and sin phi cos phi 0. So here only the rows are transformed into, rows are changed into column and columns are changed into rows. So like that it is written. So directly you will get the inverse matrix, and accordingly you will get the equation in Cartesian coordinate system, that is Ax, Ay, Az. In the previous slides, we have seen about the cylindrical coordinate system and the transformation from Cartesian coordinate system to spherical cylindrical coordinate system. Now we will see about the spherical coordinate system. First, try to understand the difference between representing the coordinates for cylindrical coordinate system and spherical coordinate system. In cylindrical coordinate system, we represent coordinates as p phi z. So p is the radius of the cylinder, phi is the angle made with the x-axis, and z is same as in Cartesian coordinate system. Now in spherical coordinate system, we are representing r, that is the radius of the sphere. Theta is the angle made with the z-axis, and phi is the angle made with x-axis. So it is shown in the diagram also, and since there should not be confusion, we are differentiating p in case of cylindrical coordinate system as a radius, and here we are representing spherical coordinate system, that is the radius of the sphere, by r, and phi is same in both the cases. Phi is the angle made with x-axis, and theta is, in case of spherical coordinate system, it is the angle made with z-axis. Since it is a sphere, there are two angles. So sphere will complete when one angle rotates in up to 25 degree, that is 360 degree, and one angle till 180 degree. So hence, if you see the range r, that is the radius, so radius in case of sphere will change from 0 to infinity. It is same as in case of cylindrical coordinate system. Theta is the angle made with z axis, so it is from 0 to pi, that is 180 degree, and phi is the angle made with x axis, so it will be from, since the complete circle, it is from 0 to 2 pi. Now representing vector in case of spherical coordinate system, so it is similar to representation in case of cylindrical coordinate system, that is AR, A theta, A phi, where AR, A theta, A phi are unit vector. Now when the point, when you want to represent, or when point you want to transform from Cartesian coordinate system to spherical coordinate system, that time these formulas you can use. R is equal to square root of x square plus y square plus z square. So it is on x, y, z plane, hence x square plus y square plus z square. P is equal to, so P in case of cylindrical coordinate system, so it is x square plus y square, and theta is equal to tan inverse of square root of x square plus y square divided by z, and phi is equal to tan inverse of y by x. So like that we can get the relation between Cartesian coordinate system and spherical coordinate system. So accordingly, these are the equations we get. X is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta. In the previous slide, we have seen spherical coordinate system, and in that we have seen the transformation. We have written the equation when we are transforming a point in spherical coordinate system into Cartesian coordinate system, or vice versa. Now in this case, we will see the vector to vector transformation. Now while transforming vector from one coordinate system to another coordinate system, here equations are written. So equations are in terms of r, theta, phi. So AR is equal to AX sin theta cos phi plus AY sin theta sin phi plus AZ cos theta. Now these equations you'll be able to understand when you see the diagram. From the diagram you will come to know that AX sin theta and cos phi. So this is the cos component, and second is the sin component, and again this is the cos component. So three vectors if you add you will get AR. So in the same way, A theta and A phi are calculated, and then the same equations are written in terms of matrix. So 3 by 3 matrix we used, and we write the equation for AR, A theta, and A phi. Now, when we want a transformation from uh, spherical coordinate system to Cartesian coordinate system, then you have to find the inverse of the matrix. So while finding the inverse, uh, what we have done, we have transformed the row into column. So if you see sin theta cos phi and sin theta sin phi cos theta are in one first row. Now they change into columns in case of second equation, that is sin theta cos phi sin phi cos theta. So like that the equations are written. So here when you find the inverse, you will get the equation in terms of r theta and phi. In the last two slides we have seen about two coordinate system. One is a coordinate cylindrical coordinate system, second is a spherical coordinate system. So in the coordinate system, representation of vector will be different. It is according to the coordinate system which we have selected, and the vector magnitude and direction will not change according to coordinate system. Only representation will be different. When we are finding the distance between 2 points, it is required in electromagnetic signal, electromagnetic waves, when it is passing through the media. That time we may require to find the distance between the 2 points. So in that case, it depends upon the distance between the 2 points. If you want to measure, then it depends upon the coordinate system which we are using. If you are using a Cartesian coordinate system, we know that general formula, that is a distance formula. D square is equal to x2 minus x1 square, y2 minus y1 square plus z2 minus z1 square. In a cylindrical coordinate system, the formula will be different. That is d square, that is equal to p2 and p1. These are the radius of the cylinder. So p2 square plus p1 square plus 2 p1 p2 cos phi 2 minus phi 1. Phi is the angle made with x-axis, and z2 minus z1, that will remain same as in Cartesian coordinate system. So in since the points are same in Cartesian and cylindrical, here in distance formula also you will get the same term, that is z2 minus z1 bracket square. In spherical coordinate system, d square is equal to r2. R2 is the radius of the sphere. R2 square plus r1 square minus 2 r1 r2 cos theta 2 cos theta 1 minus 2 r1 r2 sin theta 2 sin theta 1 cos of phi 2 minus phi 1. Here note down the angles. The theta 2 is the angle made with the z axis, and phi 2 is the angle made with x axis. So here we will see three important parameters. One is the differential length, second is differential area, and third is differential volume. Now differential length means what? The small infinitesimal length. Differential area means small infinitesimal area, and differential volume means small infinitesimal volume. So we are defining this, and then afterwards in the next chapter we are going to integrate it. So when you integrate, you will get the electric field or magnetic field in that length or in that area or in that volume. So for this reason, these three equations are important. Now here we have defined dl, that is the length small in a differential length in Cartesian coordinate system. And here since it is a Cartesian coordinate system, you will find three unit vectors, that is ax, ay, az. These are the vectors perpendicular to each other. And to understand this Cartesian coordinate system, try to visualize parallelepiped, then you will understand the equation. So dl is a differential length which is nothing but one vector which is defined in Cartesian coordinate system, and hence to define this dl you will require one vector along one component along x-axis, second component along y-axis, and third along z-axis. And then when you are adding these three components, you will get a dl. So dx, dy, ay, and dz, az. When you add, you will get dl. When you are defining a ds, so in parallelepiped also you will come to know that there are areas like dy dz in yz plane, ds dz in xz plane, and ds dy in xy plane. So when you are defining a ds for the yz plane, then you multiply by dy by dz, and vector, that is a unit vector perpendicular to yz plane, that is ax. Similarly, second equation, ds is equal to xz plane, so ds dz and vector perpendicular to xz plane, that is ay. Third equation, ds dy, that is the plane and xy plane, and perpendicular vector is az, so ds dy az. So these are the three equations obtained. Now these equations are easy to understand. Third is the dv. dv is ds dy and dz, so product of these three you will get dv. So these equations, all these three equations are simple to understand if you visualize a parallelepiped. So now if you read the equation carefully, you will come to know that if you remember the equation for dl, then you can easily write the equation for ds and equation for dv. So you should remember the equation for dl. Now why I am telling it, because in cylindrical coordinate system and spherical coordinate system, it is slightly difficult to remember ds and dv. So equation for ds and dv are very difficult to remember. Hence try to remember only the equation for dl in all coordinate system. So here in Cartesian coordinate system, if you observe, when you are finding the area, that time in the first equation, let us say ds is equal to dy dz ax. So since you are considering ax component, so in the dl equation, so in the first equation you are multiplying the components components for, or the coefficient for other two vectors, other two components like y and dy and dz. These are the component for y along y axis and z axis. So these two you are multiplying, so you are getting dy dz and ax. In the second equation you are considering the xz plane, so dx into dz, the xz plane, and multiply by ay. So in the from equation for dl, you will come to know that the remaining two components you are multiplying, and ay is the vector. So in the third equation also az is the component, so you are multiplying the other two coefficient. And while writing the equation for ds dv, so while writing the equation for dv, if you consider dl, so in the dl coefficients are ds dy and dz, so you are multiplying all three components to get dv value. So like that you can define the other coordinate system also. Like dl, if you remember, dl is equal to dp ap. Now what is ap? ap, fi, az, these are the unit vector perpendicular to each other. Now dp ap, that is radius of the cylinder, and ap is the vector along the radius. P d phi, what is p? P is the radius and d phi is the small angle. So when you multiply the radius by the angle, you will get the length of that curvature, and it is along the phi axis. So phi is the unit vector. In the same way dz az, that is along the z axis. So these three terms you obtain. So that is the equation for dl. So dl is represented in the cylindrical coordinate system. Now you can define ds and dv in the similar way. Same thing is done in case of spherical coordinate system. We are defined dl, that is dr ar plus r d zeta a theta plus r sin zeta d phi a phi, and hence you obtain ds is equal to, so multiplying the remaining term, so first we consider ar, hence the remaining coefficient we multiplied. In the second equation ds is equal to a theta is considered, so other coefficient we multiply. Third equation ds is equal to, it is the vector a phi, which is a perpendicular that is considered, so hence perpendicular to the area, so area is r dr d zeta, so it is the multiplication of the remaining two coefficient. So like that ds is defined and dv is defined. dv is the multiplication of all coefficient in the equation for dl. So in this way we have defined all three equations. So once you remember the equation for dl in all coordinate system, it is easy to write the remaining two equation, that is equation for ds and equation for dv.